Hello everyone and welcome back. So far we have looked at the different types of the signals uh, and what are the different signal transformations, how we can plot them. But now what we are going to discuss about the systems. So the first thing which we are going to look at into is the definition of a system. So what do we mean when we say we have a system? So system can be regarded as a process in which the input signals are transformed by the system in some way, and they are going to result in another signal which we are going to call as output signals. So uh, the input signal is going to be manipulated in some way, and what the system is going to do depends upon the system components. And that based upon the system components, your output signal is going to be a transformed signal of the input. And the transformation could be either linear or non-linear, depending upon what sort of operations you are performing. So when it comes to the types of the systems, the continuous time and a discrete time systems, it's very simple. We are going to call a system a continuous time system if the input to the system is a continuous time signal, and if the output of the signal is also another signal, which is a continuous time signal, we are going to call our system as a continuous time system. So normally the notations which we are going to follow is that x of t is going to be utilized for the input and y of t is going to be used for the outputs. So in the continuous time system, the input x of t passing through the system is going to result in another signal which is going to be called output signal. Similarly, we are going to call our system a discrete time system if an input to the system results in an output from a system which is also a discrete. So this is going to be called a discrete time system. So the input, any input is going to be resulting in an output, and both are going to be discrete time signals. So these are the very simple classification of a continuous time system and a discrete time system. Now, one of an important bit which we need to understand is that a system itself could be any operation. For example, let's say that our system, I'm not going to write what the system is, but let me write the y of t. So let's say y of t is simply equal to d by dt of x of t. So in this case, this particular system is simply a differential system. So what it essentially is doing is that it's taking the differential of my input signal and giving me an output signal. So that is a simple expression. So the systems are basically modeled through the equation. So now this thing is the system equation, which basically tells me how the output y of t is linked with the input x of t. So the system is going to be modeled with some mathematical expression, and that mathematical expression is going to be called as system model, or we can also call it system equation. Okay, so let's take another example of the discrete time case scenario. So we have already studied. Let me write the system first. So let's say my output y of n is basically equal to x of n minus 2. Okay, so now this particular system, what it's essentially doing is that it's shifting my signal towards right by 2 units. That is basically it's delaying my input signal. So what I can say is that this is actually a delay system by 2 units. So my system is a delay system by 2 units, and all it does is that it's going to introduce a delay or a shift towards right of the input signal. And now again, the important bit is now this particular equation written over here is basically the system equation, which is going to dictate how the inputs and outputs are actually linked. So remember, y of n is going to be this y of n we are going to use to represent the output, and x of n is basically the input. Okay. So based upon the operation, it could have been a delay system, it could have been an advanced system. Let's say, for example, if I say that my y of n is uh, x of n plus 3. So now the system is basically what it's doing is that it's basically shifting your signal towards the left. So what we can say is that my system is basically an advanced system. My system is simply an advanced system which shifts by the signals by 3 units. So that is now the definition of my system. Okay, so moving on, for any system, what we can do is we can write the equations, the mathematical expressions, and the interesting bit is that the mathematical expressions most of the times are going to have a very similar mathematical description. For example, here is an RC system which is drawn over here. So we are going to write an expression for this particular RC system and see how it's going to end up resulting in a very similar mathematical description. Okay, so if I try to write the expression, I can write. Okay, so let's look at the this particular RC circuit and try to write the expression for this one. So what we can write is that current I of t is basically equal to source voltage minus the voltage across the capacitor over R. So that is the current which is flowing through this RC circuit. And then this current which is passing through the capacitor, we can write over here IC, this particular expression for the current passing through the capacitor, and the remaining terms are going to be same. And now if I rearrange a bit, which is that I'm going to bring this C over here. So bring the C over here, and then if I rearrange it, the final expression which I'm going to get is something like this. So d VCT over d of t, and then also bring this particular term which is the VCT over RC on this side, and over here we are going to keep the source voltage RC. So now if you look closely, this particular expression basically resembles this generic expression which is d of yt upon dt plus some constant a y of t is equal to b times x of t. Okay, so this particular expression which I have written over here is first order differential equation, first order linear differential equation. So x of t is the input, b is some constant, y of t is the output. So this is the generic mathematical expression of the first order differential equation. And now if you look closely over here, what we can say is, okay, y of t is basically the output. So voltage across the capacitor is basically the output. Okay, then y of t is again over here. And from here, we can see that a is basically equal to 1 upon RC if you compare both these equations. And then B is also equal to 1 upon RC. And then X of t is basically VST, which is the source voltage, which was the input voltage. So what we have looked at is that this particular circuit, when you write its mathematical expression or equation, it turns out to be this particular generic expression, which is the first order linear differential equation. Okay, here is another example just to look at one other system. So this is an automobile system. You are applying a force and that is going to result in some velocity. So we can write the expression now. So starting from the resultant force F, m is the mass of the car and a is going to be the acceleration which is going to result. Now force is basically that the resultant force is basically F of t which is the force applied in forward direction. And then the car, there's an opposite force because of the friction, and that we are going to write as rho of V of t. And V of t is the velocity of the car. It's a function of the velocity of a car. And then this is equal to ma. Okay. And then what we are going to do is we are going to write uh, this expression again, rho V of t. This m we are going to bring over here, and then the acceleration can be written as the change of velocity, dvt upon d of t. All right. So now again we are going to just make some rearrangements, and we are going to see that what's going to be the final result. So I'm going to take all the vt terms on one side and all the remaining terms on the other side. So f of t upon m. So I'm going to write this thing over here, and then what we are left with is dvt upon d of t, which is this term, and then this term is rho times over m v of t. Okay, so now again if you look closely, what we can see is f of t is basically my input signal or input force, and 1 upon m is now the constant b, is basically 1 upon m. And then over here, if you again look at this particular side and compare it with this particular expression, you can see that, okay, v of t is basically the output signal, which is the velocity resulting from the applied force. So you have d upon dt v of t, which is the velocity. And then you have another factor, and this time now the constant a is simply equal to rho upon m. And then this v of t is again the output signal, which is the y of t. So the thing is that these are two very different systems, but once you start writing their equations and rearrange them, what we found is that both of these systems at the end of the day, their system equation models to this generic expression. So this is one of the most important motivation for the development of general tools and general mathematical expressions for analyzing and designing systems. Because many different applications are going to have very similar mathematical descriptions once you write their expressions. So now we are going to look at a few different interconnections of the systems to conclude this particular video. So when it comes to the interconnections of the systems, we can connect two systems in a different manner. So this particular connection, which is written over here, drawn over here, is basically a series interconnection. So in series interconnection, what is happening is that the output of the first system is going to be the input of the second system. So this is the input x of t, and the final output is going to be y of t or y of n. And then the output of this signal, which I'm going to call the y hat t, is going to be the input of the second system. Okay, so this is a series interconnection. So in many in practical applications, you're not going to find a isolated system. You're going to find the interconnections of the system, many systems connected together in some manner. So this is one of the example. So one very simple example where series interconnection you can find is a simple radio receiver. So a radio receiver followed by an amplifier in your cars, followed by an amplifier. So this is a simple example of a series interconnection system. Okay, so moving on, the next configuration or the interconnection of the system, which is written over here, is basically the parallel interconnection. This is an example of parallel interconnection of systems. So in parallel interconnection, the input is fed to the both systems, and then the output is basically this plus sign is basically the sum sign. So the output is the sum of these two input signals. So one of the very straightforward example of the parallel interconnection is an audio system with several microphones feeding into a single amplifier or a single speaker. So any audio system, let me write over here. So the example of the parallel interconnection is audio system with multiple microphones. So you can speak into each microphone at same time and feeding into a single amplifier or speaker. So this is an example of a parallel interconnection. Okay. And then there is another interconnection. This is basically a combination of a series and parallel interconnection. So what you can see is the system 1 and system 2 are in series, and then they are in parallel with the system 3, and then the resulting system is again in series with the system 4. So now this is a sort of a series parallel interconnection where both parallel and series connections are present. Finally, the last interconnection of the system which we want to discuss over here is called the feedback interconnection. Feedback interconnection, where the output of one system is going to be fed back into the input. So what is happening? This output of this system is basically fed back into another system, and then its output is added into the input of the system one. So it's a feedback interconnection system. And one of the very simple example of the feedback interconnection system is actually a cruise control in a car. A cruise control in a car. So if you are aware of the cruise control, the cruise control is a one of the method where you are going to fix the speed of the car, and the car is going to self-drive and try to maintain that particular speed. So what is going to happen is that the velocity of the car is going to be monitored continuously. So in a cruise control system, the car is going to simply sense the velocity of the car and adjust the fuel flow in order to keep the speed at the desired level, which you have already set through the cruise control. So that is one example of the cruise control system. All right. So these are the few ways in which the different systems can be connected with each other. And normally in the practical applications, multiple systems are connected with each other and they are all working. And you will seldom find a system which is standing alone system in the practical applications. Thank you. Bye bye.